Should do class outside today.
Yeah.
Just kidding. I'm pretty sure I failed 2 tests this week.
I haven't been asked that since.
Fine.
Would that be so refreshing?
Okay, as we get started today, I want to spend a little bit of time, just real quick. This came across my email inbox this morning. I'm a member of the American Statistical Association, so I had this email from the ASA saying, if you haven't seen this, look at it. And there was a link provided, and I clicked on the link, found this figure, so then I made a Word document out of it. But one of our U.S. congressmen showed this graph in a presentation just the other day. So this actually was up on MSNBC yesterday. This is there's an effort right now to defund Planned Parenthood. Have you heard about this?
Yeah.
Right. So he showed this graph, and then somebody called him out on it and said, "Wait, where'd you get that graph?" And he said, "Well, it came out of your report, the Planned Parenthood person. That's not our report." And it turns out it was the graph came from Americans United for Life. Right? So always remember what we talked about back then. Consider the source. Now identify for me the distortions in this graph. Stephen?
Well, the abortion number goes up by like what, a little under 40,000.
Okay.
And then
So you're looking at 289,000 up to 327,000.
and then the other one drops by like 1 million.
This one is 2 million cancer screenings down to 935,000. So down to about 1 million. So it went from 2 million to 1 million. And abortions went from 290,000 to 327,000.
But it has 289 at the same level as 935.
What? It has 289 at the same level as 935,000. And, man, talk about trying to insult our intelligence. 935,000 is somehow less than 327,000. Right? So what should this graph look like? There's one more distortion in this graph, and that is the fact that all these years are put in there, but they only have data in 2006 and 2013, right? And it's not clear at all that the yearly values would follow this line. They probably bounce all around, right?
Well, also they intersect with the main number, this number.
Yeah, they intersect. It makes it look like in 2010 they were about the same, right? Not at all true. So what should this graph look like? Not like that.
Huge amount of difference.
It should look like,
What's the comparison between abortion and cancer prevention?
I entered those numbers into Excel and made this graph myself. So here's what it should look like. Here's abortions, way lower than cancer screenings. And you do see that cancer screenings dropped about in half. And the Planned Parenthood people said, well, that's because the rules, not the rules, but the guidelines for who should be screened for cancer were changed recently, and that's true. You know, breast cancer screening and colon cancer screening, they're saying there's really not a reason to screen people under the age of 40, and most of their clientele is under the age of 40, so the cancer screenings dropped way off. But look at a number of abortions. It's pretty flat. You know, when you look at it, there's hardly any increase at all. But they drew that line shooting way up there.
What are they trying to say is the comparison? Like, if you have an abortion, you have a likely chance of being cancer?
No, there's nothing like that. What the argument is that Planned Parenthood is saying, you know, we do way more cancer screenings and other health-related things that are preventative than just abortions. And so the people that were trying to defund it were saying, no, your cancer screenings are coming way down and your abortions are going way up. And so, anyway.
And failed at it.
I'm not trying to be political, but I do want to make the point that usually when you see distorted graphs, it's some politician doing it. You can lie with statistics, right? Mark Twain once had a quote, "There are lies, there are damned lies, and then there's statistics. So you can lie with statistics. I had a fortune cookie. My daughter gave me a fortune out of a fortune cookie. We went to eat Chinese a while back, and her fortune said, do not let statistics, what did it say? Oh, do a number on you. Do not let statistics do a number on you. And that was her fortune. Hey, Dad, here you go. Anyway, there you go. All right, so today we are doing binomial distribution. We did frequency or discrete probability distributions yesterday. So today we will do the first and the last specific example of a binomial distribution. So this is a special case of a discrete probability distribution. So only under certain conditions will a random variable that is discrete follow a binomial distribution. But if it does, that's a good thing because it makes it easy to compute because it's built into our calculator. Right? So the first thing we want to do today is define what a binomial distribution is, derive a formula for it, and then we'll practice with some problems. Right? So here are there's two more conditions on the following page, but for a random variable x to have a binomial distribution, all of these things have to be met. Okay? So first of all, the experiment consists of a fixed number of identical trials. So fixed number of trials. All right? So if I flip my coin 10 times, that's a fixed number of trials. Each flip is a trial. All right? So then each trial is independent of the others. If I flip my coin 10 times, are those trials independent? Yeah. All right? For each trial, there are only two possible outcomes. Heads, tails. All right? So binomial, the word binomial, what does that mean? The bi means two. What does nomial mean?
Numbers are.
What does nom mean? Well, nom is the French word for name, right? Nom de plume. You got to be impressed. I knew that. But so two names or two categories: yes, no, success, failure, lives, dies, right? Anything like that has two possible outcomes: heads, tails. We will call them success and failure, no matter what those things are. If we're counting how many people die after they get diagnosed with a certain disease, we still call that a success. So sometimes it's not a nice thing. Then for each trial, the probability of getting success on that trial, we'll call that P. Right? Now, if those trials are independent, then that P remains constant from trial to trial to trial. So if I'm flipping my coin 10 times, the probability of heads on any flip is 0.5, and it's still 0.5 on the next flip. And it's 0.5 on the flip after that. Right? So this P should remain constant through all of the trials. Well, if you remember your complementary event rule, if P is the probability of success, what's 1 minus P? What'd you say?
0.5.
I'm not asking for a number.
Your complement.
It's the complement of a success. So what's the complement of success? Failure. So 1 minus P would be the probability of a failure. Right? But you're right, it'd be 0.5 if I'm doing a flipping coin thing. Right? All right, so then the next page says the binomial random variable x counts the number of successes in those n trials. So if I'm flipping my coin 10 times, I'm counting the number of heads that I get. I'm counting the number of successes in a fixed number trial. Right? If I count how many patients in this clinical trial die after they get diagnosed with a certain condition, then I'm counting the number of successes in a fixed number of trials. Remember, for a discrete random variable, the mean is called expected value. Right? So the mean of a binomial is n times p. Oh, cool. N times P. But wait a minute. Let's think about that. If I flip my coin 100 times, how many heads would you expect to get?
50.
50. And how'd you get that?
Probability.
No, no.
Odds.
What mental math did you do to get 50 out of 100?
Divided by 2.
Okay, which is multiplying by 1/2, right? So you took the number of flips times the probability of success on a flip, and you got the number you would expect, right? If let's say that you have a population where 25% of people say they exercise regularly, right? So now I'm going to draw a sample of 200 of this from this population. How many people out of the 200 would you expect to say, yes, I exercise? 50. And how'd you get that? 200 times 0.25, N times P, right? So that is intuitive, that the mean of a binomial distribution should be the number of trials times the probability of success on each trial. The variance is given by sigma squared equal N times P times 1 minus P. There's nothing intuitive about that. The mean, yeah, I got that. But this, you just have to know it. Right? You can derive it algebraically if you're in graduate school in statistics, but it's not real intuitive. Now, I did want to mention also that some of the homework problems, people have been asking me questions on the homework, and they're saying, it asked for the variance. You didn't show us how to compute the variance. I showed you how to compute the standard deviation. So how are the two things related? The variance is the square of the standard deviation. So sigma is the standard deviation. Sigma squared is the variance. So the variance is the thing you get before you take the square root. So the standard deviation of this, sigma, and I like to put the sub x, is the square root of N times P times 1 minus P. So on the homework for section 5.1, there was a few of them that say, what's the variance? And on your calculator, remember how to get the variance, or to get the mean and the standard deviation from a discrete probability distribution? How were we doing that yesterday? We took the x values, and in our calculator, you put them in L1, good. And then you took the probabilities, put them in L2, and then you do 1 var stats L1 comma L2. It doesn't give you the variance. It gives you the standard deviation, so then what do you have to do to answer the question? Just take the standard deviation, square it, and plug it into your Hawks system. Got it? Okay. All right, so now, what I have here, and I left my tree diagram on the board from last time because it took me a while to draw it, and I don't want to waste that time again. But this is a scenario where I have a jar of 10 marbles, and in that jar, 4 of them are black, and 6 of them are white. Right? So then I shake it up, reach in, pull one out, record the color, black or white, put it back in, so I'm sampling with replacement, shake it back up, and I'm going to do that 3 times. So x equal number of blacks in n equal 3 trials. Right? Everybody got the scenario? So here's the tree diagram for that scenario. On the first draw, I can get black or I can get white. And I've got a 0.4 probability of getting black and a 0.6 probability of getting white. Everybody see what I'm doing? Then on the next draw, if I got black on the first draw, my probabilities stay the same for black and white because I did what? I did it with replacement. So doing it with replacement ensures that those trials are independent, which is one of the conditions that we just talked about. Right? So there's your whole tree. Anytime you draw a marble, you have 40% chance of black and 60% chance of white. Right? Now, what about the random variable x? tell me for each branch what is the value of the random variable x. I'm not asking probability, but what would x be? Number of blacks in 3 trials. Top branch has x equal 3. There's 3 black ones. All 3 were black. Next one has 2, 2, 1, 2, 1. White, black, white is 1. White, white, black, 1, and 0. Right? Now, to form the probability distribution for x, we can get 0, 1, 2, or 3. Now this looks really similar to what we did at the end of class last time, where we flipped 3 coins and we counted the number of heads. Do you remember what the probabilities were? It was 1/8, 3/8, 3/8, and 1/8. Remember? If you don't, you can flip back a page in your notes, you'll probably see it there, right? Which, you start counting branches, right? So the probability of a 1, there's 3 branches out of 8 branches. So I got 3/8. But it won't work today. Why not?
There's not the same probability for drawing
Because it's
black
not
or
the
white.
same probability for black and white. They're not equally likely. So now the probabilities are going to be different. So how do I get the probability? Like, what's the probability that x is let's start at 0. What's the probability x is 0? Well, to get no black ones, that means I had to get a white one, and a white one, and a white one. And what word am I saying there that's important? And. What do you do when you have and? You multiply. So this is 0.6 times 0.6 times 0.6. So that's 0.6. Oops, I'm in the wrong place. 0.6 to the 3rd power. Right? What is a 1? Well, here's a 1. I went black, white, white. So that's 0.4 times 0.6 squared. 0.4 times 0.6 squared. And 0.4 is 0.4 to the 1st. Right? What about the 2s? Oh wait, I'm not done with the 1s. This is not the probability of getting a 1, is it? It's the probability of being on that particular branch. But there's 2 other branches that also have a 1. So I got to multiply by 3, because any branch that has a 1 has that same probability. 1.4 and 2.6s. Right? So I have 3 of those. Right? What about the 2s?
0.4 squared times 0.6 to the 1st.
Okay, 0.4 squared times 0.6 to the 1st, and how many branches? 3. Right, and then 3. Here's the 3 is up at the top. 0.4 to the 3rd, and 0.6 to the 0. There aren't any of those. What's something raised to the 0 power? 1. Right? I don't know if you remember that from algebra, but anything to the 0 power is 1. How many branches are there like that? 1. And there's also 1 branch that had a 0 and it had no 0.4s. Right? So let's do the 1 on your calculator. Take 3 times 0.4 times 0.6 squared. Do you know how to raise things to a power on your calculator? If it's squared, there's a squared button. If it's a 3, then there's a little caret button. So you hit that, and then a 3, and enter. What does this work out to be? Point what? 432. Okay? Everybody follow that? And we can do the other 3 x values just by multiplying that out, right? Well, this is the binomial probability formula. So the way it works, the probability of x is equal to the number of branches that have that combination. The number of branches. Well, that's 3 trials. Choose one of them to be a success. That's the number 3. Take 3 trials, choose 2 of them to be a success. That's also the number 3. So what if I had 10 draws of marbles and I want to know 6 successes? That's 10 draws, choose 6 of them to be a success. That number is written like this: NCX, N choose X, or combinations of N things X at a time. How many people had this in a class sometime in their, like high school or wherever? Combinations of things. That's section 4.4, which we skipped. And I said, well, we'll need it one time and I'll just teach it to you then. Right, so that's now. So this combinations thing, I'll come over here on scratch paper. N choose X is defined as this. You had exactly the same facial expression I was hoping somebody would have. She went. What does N exclamation point mean? It means N! Okay, that was a joke. That was a bad one. N exclamation point means N factorial, which I heard somebody say. So like 4 factorial is 4 times 3 times 2 times 1. Right? So you just multiply that value and all of the integers below that down to 1. That's called factorial. Okay? And it has to do with, remember we were drawing blanks and saying, well, how many ways to fill this blank, how many ways? So when the first blank you have 4 choices, the next blank you've used 1, so now you're down to 3 and so on. That's why the factorials come into play. Right? So we need to make a couple of definitions. What's 1 factorial? That's a 1. Okay, what's 0 factorial?
0.
It's also 1. That one, it just has to be 1, so we're going to make it 1, right? Because what if I say, what's the probability of getting 3 successes out of 3 trials? Then I've got an n minus x of 3 minus 3, or 0 factorial. That's got to be a 1. Right? And it works out. I mean, that's the number that makes this all work. All right, so if I have 3 trials and 2 successes, that's 3 times 2 times 1 over 2 times 1, right? 3 factorial over 2 factorial, and then 3 minus 2 is 1 factorial. And what does that equal? 3. The 2's cancel, and I'm left with 3. So there should be 3 branches that have 2 successes. And that's what we got. Right? Now it's not critical that you know how to, your calculator has a button like that. Or not a button, it has a function like that. You push the math button, then I think it's under PRB for probability, you'll see an NCR. They use an R, not an X, but NCR. So you would enter 3, then go hit that button, and then the 2, like that on your screen, hit enter, and you should get 3 back. But it's not critical because it also has this whole probability function built into it. So let's finish that. All right? Look at what I did here. I have the number of ways. That's the NCX. Then I have probability of success. What did we say that symbol was? What did we use to denote probability of success on a single trial? The probability of getting success is called P. So that's P, and it's raised to a power. What do you notice about the power on the 0.4?
I think
It's always X, right? Number of successes. So P to the X. And then this is what? What's the symbol for probability of a failure? 1 minus P. Right? 1 minus P. So that's 1 minus P to the, what's the power on the failure probability each time? You did this. It flips between whatever X is. And so if I have 3 trials and 0 successes, I must have 3 failures. If I have 1 success, I must have 2 failures. So it's always n minus x, right? Which is number of failures. So that is number of failures. The x is number of successes. And then P is probability of success. I need more room here. Probability of success on a single trial, on each trial. And finally, the 1 minus P is probability of failure on each trial. So we built this really cool looking formula, and I know you're excited about that. But you're probably thinking, God, I hope this is built into my calculator. And it is. It's built into your calculator. Right? So let's do that real quick. Take your calculator and, well, let's see, I can do this. Push the second function button and then the vars button. And above the vars, you'll see DISTR. So you're doing second function to get to that. Everybody find the vars button? It's over by the arrows. And then you see a list of probability distributions. The binomial probability is not on the first page. You have to scroll down until you get to, I don't remember what choice it is, but it's just, there's 2 of them. One says binomial PDF and one says binomial CDF. So for now, we want binomial PDF. So select binomial PDF. And the PDF stands for probability distribution function. Hey, that sounds good. And what you're going to enter is N, P, and X. The older style calculators, they give you the parentheses and then they just leave the cursor sitting there blinking. And so you have to know what you're supposed to enter. You're supposed to enter the number of trials, then a comma. The comma's above the number 7 button. Then a P, whatever your P is, and then X. Right? If you have a newer style, underneath there that'll write trials, and then P, is that right? And then X. And X is number of successes. Trials is number of trials. So it would be, for this scenario, 3.4 and let's say 2. Let's do 1. Do 1 because that's the one we did by hand over here. So enter 3.4 and 1 and tell me what you get. Hopefully you get 0.432. Okay? So it's all built in. Alright? Alright, so we're going to work some problems in a little bit, but first set of homework problems you're going to be faced with is this kind of a scenario where they'll say, determine if each scenario can be modeled with a binomial distribution. So this is the way I would set up a test question, is I would just have a paragraph and you'd have to figure out, oh, this is binomial. So first one says, selecting 3 members of a club to be officers and counting the number of officers that are girls. There are 30 members and 12 girls. Would that be a binomial setup? First condition, the first thing to check is, are we counting the number of successes in a fixed number of trials? Yeah, we're doing that here, right? We're selecting 3 members, so there's my fixed number of trials, and I'm counting how many of them turn out to be girls. So that's met, right? Then what's the next thing you have to check?
The results are, they don't lie to each other.
Independent, right? Are they independent here?
No.
No.
Because you can't set a girl back into the group once you pick her.
Exactly. Once you pick somebody to be an officer, you don't put them back in the pool and pick them again to be another officer, right? So this is sampling without replacement, which leads to dependent trials, not binomial. So number 1, not binomial. Number 2, surveying 124 people and recording their no responses to the question, do you think that internet sites should be federally regulated?
That's binomial.
I got 1 vote for that's binomial. 2, 3 votes. And 1 no. Why do you say no?
Well, it doesn't give you like what you want, like a success kind of thing.
Well, we're counting the no's. So that's a success.
Yeah, but like on the other one, it gives you like 3 numbers and this one just like 1.
Oh, you mean it's not giving the probability of that? That's true, it's not. But suppose they gave us that in the population, the probability that 60% of people would say no to this. Now you take a sample. Would that be binomial? Technically, no. Because when you do a survey, do you sample with replacement or without replacement? Without replacement. But I put this one in myself as an example, as a point, that if you're sampling without replacement, they're technically not independent, but the change in probability from one draw to the next is so slight that you can ignore it. You say it's negligible, right? So if you're sampling U.S. citizens, there's 330 million Americans, and you're going to draw 124 of them. So when you get one person that says no, now there's 1 less in the population. So the probability changes, but it changes so slight that it's out to the 8th decimal place or something, right? So we would treat this as binomial. All the other conditions are met. Okay? Okay, number 3, rolling a die 20 times and recording the number of spots on each roll. Is that binomial?
No.
I got like 3 people that are shaking their heads or whatever, and everybody else just staring at it.
There's more than 2 possible outcomes.
More than 2 possible outcomes. This is not binomial. Okay? Rolling a die 20 times and recording the number of times a 1 is rolled. Yeah, now it's binomial. Hey, there's still 6 outcomes, but I've collapsed them into a 1 is a success and anything else is a failure. So I've made it into 2 outcomes. So it is binomial. They're going to be independent rolls. We've got a fixed number of trials and so on. All right? Last one, counting the number of times a coin is flipped before the first head occurs. So I flip my coin, tails. I flip it, tails. I flip it, there's heads. So my answer is 3. Is that binomial?
There's no fixed number of trials.
There's no fixed number of trials. That's right. It's not binomial because the number of trials was not fixed in advance. Got it? So you'll have some like that you have to practice with. Okay, so let's go to this one. Oh, you know what? I never did finish this out, and it's really not necessary to do that. But if you did each one of these using your binomial PDF, how would you confirm that it is indeed a probability distribution?
Well,
they should all add up to 1, and they should all be between 0 and 1. Right? And it will. Okay? So now, let's look at this example up here. A quality control expert at a large factory estimates that 10% of all batteries produced are defective. If he takes a random sample of 15 batteries, what is the probability that exactly 2 are defective? How would you solve that problem?
I know because you see it.
Okay.
Estimate how many might be detected overall. Do that first.
Okay. I like this example because this is exactly how I would put one on the test. Right? Only when it's in, it has a title up there, calculating a binomial problem. There's a big sign that says, here comes a binomial problem. But on my exam, I'm not going to be that nice. I'm not going to have a neon sign that says, this next one is binomial. It's just going to have that paragraph. And you have to figure out, ooh, this one's binomial. And then I might have one about the committee member, the officers from a club, and that one was not binomial. And you got to know, this was not binomial, so I can't use binomial PDF. This other one is. You have to be able to distinguish. So get good at telling when you read it whether it's binomial. So we know this one is binomial, but what are the tip-offs?
There's a
Number of trials.
Okay, the fixed number of trials. What is the number of trials?
15.
15. Okay?
There's a clearly defined success.
Or failure, it's either defective
Okay,
or
so
it's not.
n equal 15, fixed number of trials. Success,
It's a failed battery.
okay, is a defective battery. So it's a success to get a defective battery. Right? So 2 possible outcomes. Success, failure. Defective, not defective. Right? So that's met. So 2 outcomes per trial.
And they're dependent.
They're
Independent.
They have to be independent. Would these be independent? Does selecting one randomly and checking it, does that influence the probability of the next one? No. We have to make an implicit assumption here, and it's the sampling without replacement issue that we just talked about. When you sample, quality control sample, do you sample with replacement? You find it's defective, so you throw it back in, and you sample it again? No, you sample without replacement. So technically, they would be dependent. But we have to make the implicit assumption that we've got a large number of batteries that we're choosing from, and taking a relatively small sample of 15 isn't going to change the probabilities. Plus, they're making new batteries all the time and keep dumping them into the population, so we're okay there. So we can consider them independent events, even though technically they're not. Okay? The standard rule of thumb, and I don't think this is in the book, but as long as you're sampling less than 10% of the population, then you don't really have to worry about that. Okay? All right, so then what is P?
10%.
10% or 0.1. Right? So P is the probability of success on any single trial. So when I grab a battery, there's a 10% chance it's defective. So that's P. Okay. So now compute the probability of that. Do it yourself, and then I'll come around and look at it. I'll tell you what, I'm going to put this where the video will show the screen. I think they can read that. What do you got? You got one number entered wrong. You got, okay, that's correct. Okay, good. Good. All right. Yep, that's right. 266, yep. you should see 0.266 something or other. Is everybody getting that?
Would X be?
That's the next, I didn't write it down, but what the heck is X? X is number of successes you want the probability for. And it's 2. What is the probability that exactly 2 are defective? So there's your X. Okay? So you're going to do binom PDF at 15.1 and 2, which is 0.266.
8, 9.
8, 9, so we'll call it 9, like that, right? Okay, so always round probabilities to 4 decimal places. More than that's overkill. Less than that is not good, so go to 4. Right? Any questions on that? All right. Then almost the same problem, but this time it says, what is the probability that no more than 2 are defective?
So would X be
No more than 2 are defective. So before we had probability that X equals 2. How do I write this one? Probability that X
Greater than 2.
no more than 2.
No,
Less than or
sorry.
equal to
Less than or
2.
equal to.
Less than or equal to 2. That's right. And people get confused by that, and sometimes in the heat of the battle on a test, you get in a hurry, and if they say things like, at least 3, or no more than 3, or no less than, you got to figure out, okay, make a mathematical expression out of it, then it makes it easier to figure out what do I put in my calculator. So how are you going to work this? What does that mean? Less than or equal to 2?
2, 1, or 0.
You got a 2, you got a 1, or you got a 0. And the word or, you add, right? So addition rule. They're mutually exclusive events. You can't have both a 2 and a 1 in the same sample. So you could just do it 3 times, 0, 1, and 2, and add them up. You'd get the right answer. But the calculator actually has built into it a more convenient way to do this, and that's the binom CDF. PDF stands for probability distribution function. CDF stands for cumulative distribution function. So this one you can do with binom CDF at N, which is 15, P, which is 0.1, and 2, which is my X. I don't know if that really shows on the screen when I write it over the top. So again,
So for a test, if we had something like this, and you wanted to show the work, we just write binom CDF.
yes, show your work by writing that. Then I can see, well, what did they enter? And sometimes I say, oh, they entered the wrong P or whatever, and you might get most of the credit. But
So for your X value, you don't do 0, 1, and 2, you just put 2 and then it knows that it's less than?
as long as you do CDF, then it's a less than.
So if it was greater than, is
That's the next one, right? What's the probability, and I won't show it on the screen, let me just write down the next question. What is the probability of at least 3?
I guess you could just do 1 minus.
Actually, let me make it a 4. I don't want to keep having this 2 pop in there. What's the probability you get at least 4 defectives in your 15?
CDF for 11.
That's a thought. One thing you could do, I would not recommend, but you could say, well, at least 4, that means probability that X is what? What does at least mean?
4
4 or
greater.
greater. So greater than or equal to 4. So you could say, well, I'm going to do my binomial PDF at 4, then I'm going to do it for 5, and then I'm going to do it for 6, and I'm going to do it all the way up to 15. I'm going to add all those numbers up. I don't recommend that. That'd be the only problem you got done on a test. Okay? Can we take advantage of our binomial CDF? CDF only does less than or equal. It does not do greater than or equal. But what can we do? You said it. Could we do,
11.
you said something about 11, right? What's it? Complement. He's doing the complement. What's the complement of at least 4? If you didn't get 4 or more, you must have gotten 3, or don't say at least 3. You got at most 3. The complement of at least 4 is at most 3. But again, all those at most and at least and that just makes my head swim. So it helps me to write it out with an expression. What's the probability? Remember, probabilities of complements are 1 minus. So 1 minus the probability that x isn't greater than or equal to 4. If it isn't greater than or equal to 4, it is less than or equal to 3. Now, you may have thought, well, the complement is less than 4. The complement of greater than or equal to 4 is less than 4, and that is correct, but your calculator doesn't have a less than function, it's got a less than or equal function, so then you have to drop that to a 3. But since it's a discrete random variable and only whole numbers are possible, then less than 4 means the same thing as less than or equal to 3. So then you would do 1 minus binom CDF at 15.1 and 3. Most common mistake on a problem like this is leaving that as a 4 and putting a 4 there for your x because that's what the problem said. It had a 4 in it, so you just put a 4 there. But you got to remember, well, when I do complement, and calculator wants an or equal, I have to drop that by 1. Right? So this is x minus 1.
But once you solve that out, that's your final.
And then once you get this, that's your final answer. Another really common mistake is to forget the 1 minus part. Right? And they'll even have it written on their test paper, 1 minus binom CDF, but then they'll give me an answer that's just the binom CDF part. But you can type it in like this. You can type a 1 minus, and then go second function, DISTR, binom CDF, and it'll put it on your screen just like that. You can do it all in one step, and then you don't forget to go back and then take 1 minus your answer. Okay? All right, so to summarize all this, this PowerPoint presentation is already posted for you out on D2L. And I added this slide as the last, I need to move it up so the whole thing is showing. But I added this slide at the end just as a summary of the calculator functions, right? So if you have a binomial problem, and remember, it has to be binomial before you use all these fancy functions. But if you have a binomial problem that's exactly equal to some number, then you use binomial PDF. If you have a binomial problem that says less than or equal to some number, and a lot of times they'll say at most, and that means less than or equal, right? So no more than, or at most, then you'll use binomial CDF. If you have an at least problem, right? Probability of x greater than some little x, greater than or equal to, then you'll use a complementary event, 1 minus the probability that x is less than or equal to 1 less for your x. Right? All right. That's all I know about that. We will see you on Friday. Don't forget you have section 5.1 homework due tonight by midnight, and this 5.2 will be due on Friday night. So we'll see you then.